Evan?
When we were doing the calculations of the electron's mass,
Yes.
and we put the total charge was the amount of electricity that went through the entire, that went through the wires,
Yeah.
was, so the amount of electricity that went through the wires, that total charge is equal to the total amount of charge of the, sodium?
Right.
Is that?
Right. So each sodium atom, each positive sodium atom, carries a certain amount of charge, and the total number of sodium atoms that react have to be equal to the total charge that went through the whole circuit.
Oh, so this is the, you know, this amount affects 1 mole of.
Yeah, in my
sodium
example,
atoms.
one atomic weight, 1 mole of sodium reacted and produced a certain amount of charge. Well, if we know the charge on each sodium atom, and we know the total charge, we can figure out the number of sodium atoms that had to react.
So when you use a mole, so 96,500 coulombs, if you ever separate a mole of atoms and they're going to split single into
Right,
single
right.
charged
Single.
atoms, that is how much electricity you're going to have?
Absolutely.
Okay.
And so, you know, one mole of hydrogen atoms that reacts will produce that same amount of electricity. I mean, so 1 gram of hydrogen will produce the same amount of electricity as 16 grams of oxygen or 23 grams of sodium, so on. Ben?
Do you know if you can make a generator that could generate the electricity? And
Make a generator
generates the electricity?
generate which electricity? I mean, we've covered electric generators that generate electricity, right?
Yeah.
Just from motion.
Like a battery or something?
Yeah, I mean, you can generate electricity in several ways. One way is, the first way they discovered is just from chemical reactions. Now, that's what's going on in a battery. But then we covered Faraday's discovery that you could also just turn a coil through a magnetic field, right, and generate a current that way.
I was just thinking
But
maybe you could do it small enough to like fit into like an RC car or something.
oh, fit an electric generator that fits into a car?
Yeah, like an RC car, like a remote control car.
Oh, yeah, you could do that.
So it would continuously generate electricity. So
Hmm?
it would continuously generate.
I mean, you have to have an energy source that turns. I mean, if you could get a crank turning that could generate electricity, but see what you really want is in a car is something that will make the wheels turn, right?
Yeah.
So, I mean, electric cars are. I mean, they run off of batteries, right? So, I mean, in that case, what you're doing is using the chemical reaction to generate electricity and then turning that into motion.
Yeah.
But okay, let me get to what I want to tell you about this afternoon. First, I need to issue a couple of disclaimers. The first is on a mistake I made this morning. When I gave you that example of electrolysis with regular table salt, sodium chloride, well, you might have noticed, based on what I've told you before, you could have noticed something that was wrong with that example. I told you that sodium was highly reactive in water, so you wouldn't have sodium metal just building up on this plate. Which is sitting there in water. So I oversimplified that reaction. But it still the main point I was making still remains true, that the number of sodium atoms that underwent the chemical reaction in that electrolysis process, if 23 grams of sodium underwent a reaction, you would get that amount of electricity. But I should have used a different example where you really would have a metal just building up on the plate. But you have to use a metal that's non-reactive in water. For instance, if you used, instead of table salt in that reaction, if you used, there's a compound called silver nitrate that dissolves in water. And there you would have 1 mole of silver just building up on the negative electrode. Yeah, Troy.
Did you do electrolysis that way, or just like what would happen?
Well, I mean, what would happen, actually, I'm pretty sure what would happen. I've never done it. I'm not a chemist. But I think what would happen is the sodium would react with the water, and what you would get is hydrogen bubbling up at the negative electrode, rather than sodium just accumulating on the plate. So, okay, let's get back to thunderstorms and lightning and what I started to tell you about at the end this morning. So I was talking about atmospheric electricity and lightning. And what we established this morning was, or what I told you about, was that the surface of the Earth is actually negatively charged. And the atmosphere, at least high up in the atmosphere, is positively charged. And so there's this continuous stream of current, actually, coming down to the Earth. And in fact, all of you right now have, you're all charged negative. You have billions of extra electrons all over your bodies right now. And in fact, if that weren't true, then you'd be in trouble, because as soon as you touch the things around you that that have all those electrons, you'd get a big shock. So it's a good thing that you're negatively charged, like everything else around you on the ground. Yeah, true.
So is that why when you go down a slide and you touch anything, it shocks you because you get a current loss or something?
Well, that's just the static friction electricity that we experience is whenever there's a difference between the charge on you and the charge on whatever it is that you come in contact with. But under normal circumstances, everything here on the ground, on the Earth, is negatively charged. Yes? Nick?
You became positively charged, and you didn't, and for some reason you didn't get really shocked. Would you weigh more?
Oh, would you weigh more? No, you'd actually weigh slightly less. Because what is actually being transferred among objects under ordinary circumstances is electrons. And they're negatively charged. So the way that I could make you positively charged is by drawing the electrons off of you. And then what would be left is the positive you. But I would have drawn a small amount of mass off of you by taking those electrons away. Okay, let me see. I raised a question at the end of this morning's class, that if the Earth is negatively charged and the atmosphere is positive, and there's this constant current coming down to Earth, you would think that the Earth, everything would equalize after a while, and the Earth would just discharge, right? I mean, there's, I gave you that incredible figure of the total current running from the atmosphere to the Earth's surface is 1,800 amps. So 1,800 coulombs of charge every second is running down to the Earth's surface, this positive charge. And you would think it would discharge the Earth's negative charge after a while. And in fact, if you work out the numbers, at that rate of 1,800 amps, the Earth should discharge after an hour, or less than an hour. So and it doesn't. Okay. So what's going on? There must be some other process that is charging the Earth up. And that other process is thunderstorms and lightning. They have the effect of charging the Earth up. In fact, all the billions of extra electrons that are on your body right now came from lightning strokes. So, yeah, Nick.
But isn't there like at least an hour of time that there's no thunderstorms?
Ah, good question. What if we went an hour without any thunderstorms anywhere on Earth? The Earth would discharge completely. Okay? Guess how many, I mean, if you take the entire Earth, scientists have estimated how many lightning strokes per second are there? Any guesses? 100. It's roughly 100 lightning strokes per second. If you take all the thunderstorms everywhere on Earth, because there's 40,000 thunderstorms per day. Oh, I don't know how many people get struck by lightning, but I mean it's not that uncommon. In fact, I've heard of like clubs of people who have been struck by lightning. You know, they get together and reminisce and talk to each other, I guess. Yeah, so it's not that uncommon. Yeah, Troy.
In 1 volt of lightning, about how much charge is there?
Oh, yeah, it turns out to be about 20 coulombs, which is a lot of charge. Now, maybe that doesn't sound like a whole lot, but a lightning stroke is actually very quick. So it takes a lightning stroke takes about a thousandth of a second. So the actual peak current in a typical lightning bolt is close to 10,000 amps, which is a big current. Okay, so it's only 20 coulombs of charge because it's over so fast. But you've got this thousandth of a second current of 10,000 amps. Yeah. Yeah.
So, how come lightning doesn't occur when the sky is not cloudy or blue?
Okay, that's a good question. So let me go into what is actually happening in a thunderstorm and what produces the lightning and why it ends up with this negative charge coming down to Earth. So let's look at thunderstorms. Now, it took scientists a long time to figure out what was going on in thunderstorms, and they think they've got a handle on it now, but I don't know whether this theory I'm about to tell you is actually considered proven or whether it's just the best theory. I mean, I read about it in a book that's now about 40 years old, so you might be able to find even better stuff on the internet right now. But The 40-year-old book that I have, this is the way they explain it. In a thunderstorm, you've got what's different about the air than normal. It's wet, right. Now, in general, in the atmosphere, you've got warm air down near the surface, right, and cold air higher up in the atmosphere. I mean, the temperature goes down pretty quickly as you go up in altitude. Well, now you know that, or you probably know that warm air rises, right, relative to cold air. Now, if the air is dry, then as the warm air rises, it cools off. So there's just equilibrium between the warm air and the cold air. But something else happens when the air gets wet. If you have warm, wet air down here, and it starts rising, well, we know that water has a tremendous heat capacity, right? It tends to hold on to the heat that it has, and it has a lot of heat. So it doesn't cool off quickly. So when warm, wet air rises, it doesn't cool off as fast as warm, dry air. It stays warmer for longer, and so it keeps rising. So you end up with this warm, wet air going up very high before it finally loses its heat. Now, so you end up with a bunch of, eventually it cools though, and eventually you get cold, wet air. Now, when it finally does lose its heat up here, you've got all this heavy water up high in the atmosphere. Yeah, Nick. Excuse me?
Is this normally why it's really deep?
Yeah, that is part of the reason, because as this warm, wet air gets sucked up, it creates an updraft, and it actually sucks in air from the sides. Yeah, so this is it's an unstable weather region that causes winds too. Now, but eventually, like I say, this wet air cools off. Now it's up really high, and it's finally cooled off, and Daniel's predicting that it starts coming down now. Now, here's the interesting thing that happens, though, when it starts coming down. Let's look at a particular raindrop. Okay, I'm going to exaggerate its size a little bit here. Yeah, Nick. Oh, it's not so much friction, but it does have to do with these negative and positive charges that I told you about earlier. Remember the surface of the Earth has these negative charges. And up here there's more positive charges. Okay? So what is that? How does that affect this raindrop that starts to fall now? Now, this drop is not, at least when it starts to fall, it's electrically neutral. It doesn't have any charges on it. But it becomes, because there's an electric field here, okay? You remember, because there's electric forces here, just because There's all these negative charges down at the surface and positive charges up in the atmosphere. What is that going to do to the charges in this little raindrop? Well, it's going to attract the negative charges up here to the top of the drop and positive charges down here at the bottom. Okay, so the drop is still, I mean, at the beginning anyway, it's still neutral, but it becomes what is called polarized. Okay, there's some negative charges tend to go to the top, and the positive charges collect on the bottom, just because of the forces due to the negative Earth and the positive atmosphere. Okay. Now there are charges roaming around, ions roaming around in this atmosphere. So what's going to happen? Now, let's say we have in this atmosphere here, in the path of this falling water drop, we have a couple of ions. One of them is positive, and one of them is negative. Okay, and this thing's falling right toward them. Yeah.
How big are ions?
Oh, they're not very big. I mean, they're tiny compared to the water drop. I mean, they're just molecules that are charged. Yeah. So. Oh, you know, the typical ion in the atmosphere that gets collected by these raindrops, I'm not quite sure what they typically are. The book I read called them heavy ions, which seems to indicate that they're not normal air molecules that have been ionized. So I don't. They're probably heavier molecules that make up a small contaminant in the air. But if we have these ions in the air, and our water molecule is falling into them, now the ones that are positively charged, okay, they're going to be repelled by the bottom surface of this water molecule that is also positively charged. So this guy is going to, get shoved out of the way by the electrical force, while this negative ion is going to get attracted. Try.
Won't that positive, if the positive gets shoved down, would it, if it was shoved to the side, wouldn't it also be attracted by the negative ions?
Oh, well, it'll be shoved down, but as it'll actually be shoved, I mean, as I've drawn these, where the location of these charges are, it would be shoved in that direction. But it gets shoved out of the way. That's the point. So as these water droplets fall, the bottom line is they pick up negative charges because their bottom surfaces are charged positive due to the electrical forces, due to this negative charge on the Earth. So as these raindrops drift down from the top of this thundercloud toward the bottom, they pick up negative charges. So the net result of this is that if you have a thundercloud, there's my thundercloud. You will end up with the bottom part of that cloud being strongly negatively charged. Just by these raindrops that have positive charged bottom surfaces falling through the atmosphere and picking up these negative charges. And, yeah, Troy. Yeah, it would be if it were, if it were light enough to move, but it's heavy enough so it stays there. And it turns out that this process makes the thundercloud charged much more strongly negative than the Earth's surface is. And so lightning is actually negative charge running off this thundercloud to the Earth's surface, which is charged negative, but much less so than the thundercloud. And that is, this lightning, like I said before, the average lightning stroke is about 20 coulombs of charge. And it consists of electrons running off the bottom of this thundercloud to the Earth's surface. Yeah.
Why do they go down? Are the electrons just being pulled? Are the electrons being pulled down by gravity?
No, not being pulled down by gravity. They're being pulled down by, it's the exact same thing that happens. You had a Van de Graaff generator, right? So, and you charge it up really strong, and you put your finger too close to it. There's all these electrons are on the bottom of this cloud, and they don't like to be that close together, right? They're all negatively charged. So you've got this tremendous amount of negative charge on the bottom of this cloud that wants to get away from the rest of those negative charges. And all it takes is a pathway. If the air starts to ionize, if the electric field gets, if the electric forces get strong enough to strip some electrons off these air molecules, and so there gets to be some charged particles in the air here, that gives all the electricity in this cloud a pathway to follow. And it just, it's exactly like your Van de Graaff generator or, a balloon that you rub on your head. It gets a lot of charge on it, and if you get an opportunity to jump off, it will. And that's exactly what's happening here with the lightning stroke. So 100 times a second, there's 100 lightning strokes per second over the Earth, and each one of them on the average is dumping 20 coulombs of charge. You can figure out how many electrons that is, by the way, right? All you'd have to do is divide by 1.6 times 10 to the negative 19th, right? That's a lot of electrons. And that's what's charging up the Earth.
About how many coulombs would it take to go through a light bulb for a day?
Oh, that's a good question. Let me see. If we have a 120 volt source powering a 60 watt light bulb, okay, that is half, what? Yeah, it's half an amp, right? Okay, so it's half an amp to power a, Right, well, if I make it a 120 watt bulb, then it's 1 amp, okay? So, well, actually this morning we did a calculation where I showed that if you did 1 amp for a day, that comes to about almost 100,000 coulombs. So the yeah, actually, so it's not that much electricity, is it? Let me see. It's for the lightning. We said the total electricity from lightning that is charging up the Earth is about this 1,800 amps. So, and a normal light bulb, you could have 1 amp. So, 2,000 light bulbs, you'd have the amount of electricity that that you get, on the average from thunderstorms. Yes.
When you talk about something being neutrally charged, that just means it has about the same number of electrons as everything around it. So something neutrally charged.
Right. Now, so far, okay. So far, I've told you that there are these negative particles in atoms, but ordinary matter is electrically neutral, right? So if there are negative particles that are making up at least a part of this atom, clearly there have to be some positive particles too to balance them out, right? Because most, when I say something is electrically neutral, we've proven in this course that matter is made up of particles. So when something is electrically neutral, that means there's equal numbers of negative and positive charges. Now, I haven't told you anything about the positive charges yet, but I'm going to. Next week is when we're going to talk about that. But yeah, when I say something is electrically neutral, it's equal numbers of positive and negative charges. Okay. So anyway, that's. I thought it would be lightning. Thunderclouds are. This is some interesting physics. Interesting that scientists were able to finally understand the phenomenon that Ben Franklin started out investigating. And we've got, based on our knowledge now of atomic theory and a lot more knowledge of electricity than Franklin had, scientists have actually been able to figure out the way in which thunderstorms actually charge up the Earth, and then that charge is dissipated in dry areas. Okay, so notice what's going on here. You have a negative charge flowing down to the Earth in these in the thunderstorms, and then in the dry areas, you've got the Earth discharged in effect by positive charges coming down from the atmosphere. So it keeps the same amount of negative charge on the Earth, on the average. You've got the Earth being charged up in storm areas and discharging in dry areas.
What's the mechanism for the dry area charge transfer?
Oh, just the attraction of the positive ions in the air to the negative Earth.
They just lift up the electrons?
I think the ions themselves actually come down to Earth and grab an electron. but
In the form of like dust or something? Or air?
yeah, or cosmic rays, and
Oh.
yeah, I'm not sure. The article I read on this didn't go into the details. Okay, well, we can barely get started on the last thing I want to tell you about, which is I've told you about electrons now, but obviously they are not the only particles in atoms, because like I say, they're negatively charged, and atoms are usually neutral. So now we have to look for some positive charges that are in atoms. Yes, Daniel? Protons, that's what we're going to find, but not right away. So call this section Discovery of the Atomic Nucleus. Now, the first major step toward this discovery was made by a French physicist named Antoine, how do you spell his last name? Becquerel in 1896. Now, Becquerel had this, people had noticed that if you hit certain materials with a beam, you know, they would glow. Okay, we saw this in the discovery of the electron, right, where we had a glass tube and they drew out this negative beam of electrons that flew down the length of the tube, and when they hit the end of the tube, you saw a green glow. I mean, you saw the end of the tube glowing. That's how they knew there were these this beam. Nick, you look confused. Oh, so that's new to you. Oh, okay. Yeah, we covered that. Get the tape. So now Becquerel had the idea that for testing certain materials, and his idea was, well, if we hit them with concentrated sunlight, he thought that certain materials should send out beams of something. Okay, now he was testing this, and the way he decided to test it was he had this photographic plate that was covered, okay, not exposed to the sunlight. And he put a certain salt material on top of it that he got lucky in his choice. It happened to have some uranium in it. Okay, and he focused some sunlight on it, and then when he developed his plate, he did notice that the plate, the photographic material had been exposed right in the shape of this uranium salt that he had against the plate. In other words, the uranium salt had been emitting something that, even though this plate had been covered up, okay, so the sunlight couldn't get to it, whatever that uranium salt was emitting was strong enough to get through the cover and expose the photograph anyway. So he thought, okay, I'm on to something here. You know, if so he decided he was going to do this again the next day, double check it. Well, it turned out the next day was really cloudy. So he couldn't focus sunlight on his uranium salt and do the experiment he intended to do. So he just stuck his covered up photographic plate in the drawer along with his uranium salt and waited for a sunny day. Well, it stayed cloudy for a while. So just on a, just for the heck of it, he got impatient waiting, and he decided just to develop the photograph to see if anything was on it. Sure enough, the plate was exposed. The photograph had been exposed, and he hadn't hit it with any light at all. I mean, this uranium salt was emitting this stuff that exposed the the photographic material, whether or not there was any sunlight around or not. So that was the first major discovery that certain materials, uranium was the first that he discovered, but then it was shortly after this that a couple of other French physicists, the Curies, discovered a material called radium that emitted even more of this stuff. Okay, so whatever the stuff was. Now, they didn't know. Yeah, Nick. Yeah, this is the discovery of radioactivity. So what they found was uranium, radium. Actually, radium works even much better than uranium. And certain other heavy materials say spontaneously emit, well, what do they emit? Well, they didn't know much about it at first at this point. They just called them alpha particles. Didn't know what alpha particles were at this stage. Yeah, yeah.
Did people have access to large amounts of these?
Yeah, the Curies actually, I mean, uranium isn't hard to find. You can get that in large amounts. There's, well, I know there's one place up in eastern Canada. There's a big uranium ore deposit. I mean, it's not pure uranium that you find in nature, but you can find places where the rocks just contain a large amount of uranium. And so uranium is mined. You know, it's like gold or silver.
How do you get pure?
Hmm?
How do you get pure?
Oh, chemical processes that can separate out the uranium from the other stuff. I mean, I don't know exactly how they do it. Yeah. Oh no, not at all. No, uranium's tame stuff. I mean, you can hold a chunk of it in your hand; it won't hurt you really. I mean, it's the uranium is radioactive, but it's not enormously radioactive. I mean, if uranium were that dangerous, believe me, the Curies would have been dead because they worked with a lot of uranium, and I mean they did get exposed to too much radiation. But the main reason they got exposed to so much radiation is because they well, I'll finish this up quickly. But some of their uranium samples, they noticed seemed to emit way more of these particles than they should have. And it's because they had radium in them. and radium's even much more strongly radioactive than uranium. So I'll continue this. Yeah. Ben.
So uranium, when it's like struck really hard, is it, or when something blows up?
Oh, well, I'll explain to you about nuclear bombs after next time. I mean, uranium can be used to make a really, really powerful bomb. I'm sure you've all heard that, but you have to do something very special to it before it can blow up on you.
Isn't there also like uranium bullets and stuff for like?
Yeah.
Like,
Yeah, but they aren't